Hello students, welcome to the Gate Academy again. So guys, today is the last score booster session for theory of machine. Okay, so आज हमारा theory of machine का last score booster session है. Hello Sam Prashant, very good evening to you. Very good evening to you. So guys, today is the last session of our score booster of theory of machine. Hello, hello, hello. So guys, in today's session, in the last session up to what we have completed, so today is the third session of theory of machine, and I hope that all of us have watched. Shamprashan, we'll try to. Okay, we'll try to do that. Okay. So guys, in today's session, in the last session, very good evening, Pranjali. In the last session, beta, what we have done? In the last session, what we have done? We were seeing the flywheel thing, and we have solved a few questions of flywheel, and we have come to this point that in any question of flywheel, we ultimately have to use this formula. Right? We ultimately have to use this formula. Delta E max is equal to I omega square CS. Very good evening, Keshav. Okay, I omega square CS. Okay. We have to use this formula. Okay, at the very end. Now we have seen in the last session one type. Okay, so we have seen a type 1. Okay, what was our type 1 in the last session? In which delta E max is directly given in the question, right? What was the type 2? Okay, what was the type 2? So the type 2 was the one in which we have been given with T theta diagram. We have been given with the T theta diagram, right? This was very good evening, Gautam. Okay, so we have deal with it in the last session. Now coming to the type 3. Okay. So in this type 3 question, so we have T given as a function of theta. There may be some problems in which, so we have the T theta diagram. What does this T theta diagram shows us? That it shows the variation of torque with respect to the theta. Okay, with respect to the crank angle, to be more precise. Okay. Now this variation can also be given in terms of a function. Okay, so in some questions like this, okay, we are given with a function of t, okay, like this, as you see it, okay, as this. So here t is given as a function of theta. Okay, now here in this kind of a question, what is to be done and how we can approach and find delta E max? And as we are aware, once we find the delta E max, we are able to solve the question very easily, because it's just a matter of one more formula. Now can you please try to solve it? Okay, so you have to solve for the 3 parts. The data is given to you. Okay, you will have to find the power developed. Okay, so find the power developed considering n is equal to 100 rpm. You can consider the n as 100 rpm. Okay. Okay, so mean speed is given actually. It is 180 rpm. Na? Okay, so you consider mean speed as 180 rpm and try to solve this. Okay, let's try to solve this question. Let's see if we can solve it or not. Please try solving it. So today is our last theory of machine score booster session. From tomorrow, I'll be beginning with industrial engineering. Okay. Very good evening, Dheeraj. Welcome again to the session. Let's try solving this one. Any answer? Let's see if we can solve it or not. Very, very simple question. See, you have to follow the same procedure. Okay, so in the last session, what we have learned, in the last session, we have learned that the first step to find the delta E max is finding the work done in a cycle. Okay, so how did we find the work done in a cycle in the last session? We find it by finding the area under T theta diagram, right? Now I hope that we understand that area, finding the area in some diagram means integration. If we say it mathematically, so integration is something which we refer to as finding the work done per cycle, okay, or finding the area, right? So the first thing you have to do, you have to integrate this relation. So let's see. So we have T is equal to 20,000 plus 9,500 sine 2 theta minus 5,700 cos 2 theta. So this is my curve. This is my equation of T, right? This is my equation of T. Now, obviously, we have to integrate it because we find the work done by integration. So, work done per cycle, now to integrate it, we require some limits, okay? In which limit we have to integrate it. Now, how we can find the limits here? How we can find the limits here? So, we have sine 2 theta, so the cycle of sine goes to 0 to 2 pi. Okay, so we can write it like this. Sine cycle is up to 2 pi. So 2 pi, you see this coefficient, that is 2. And for this cos 2 theta, cos cycle goes to 0 to 2 pi. Okay, cos function repeat itself as 2 pi again. So we'll have to write this denominator. Whatever coefficient is there with the theta term, we have to write in denominator. Okay, so this will become pi by 1. So if I write it, okay, for this will become pi by 1. This will become pi by 1. Now you have to do what? You have to take whatever fractions you are getting this way. Let's suppose there may be some more trigonometric ratio out there. Okay, like let's suppose if tan is also there. So tan cycle goes to pi. Okay, tan cycle goes up to pi. Okay, so you will have to write that fraction, and whatever fractions you are having, you will have to take the LCM of numerator divided by HCF of denominator. This is all you have to do. You have to take the LCM of the numerator and HCF of the denominator. So if we take the LCM of the numerator, we'll be getting pi, okay, and HCF of the denominator, that is 1. So that means the cycle of this function, that means this function repeat itself after pi, okay, from 0 to pi. Now if we integrate this, I'll be getting 20,000 into pi. Is this fine to you? Please answer me. Please answer me. Please answer me. Work done per cycle goes to 20,000 into pi, right? If we integrate it, I think we'll be getting the same thing. Okay. Okay. So we have got the work done per cycle. Now how we can get the mean torque? So mean torque is work done per cycle divided by the length of the cycle, which is here in this case is pi. So basically we are getting 20,000 Newton meter. Is it fine to everyone? Please answer me. Is it fine to everyone? Okay. Now there is one quick thing also. So if you see this relationship also, T is equal to 20,000 plus 9,500 sine 2 theta minus 5,700 cos 2 theta. So if you see this kind of a relationship without any integration and without following this step, you also can say that this is your T mean. Sir, how we can directly say? Because we know that the torque, mean torque refers to the constant torque. Okay, so here in this relationship, if you know a little bit about plotting some equation, okay, so this equation, this 20,000 is having no sine or cos component multiplied to it. Now, when it is having no sine or cos component multiplying to it, that means when you plot it, it will be plotted like the straight line. Okay, so what I am trying to say, whenever you see this kind of a equation, the term which is having no trigonometric ratio multiplied to it, the term which is having no trigonometric ratio multiplied to it, you can say that is directly your mean torque. Please answer me if it is clear or not. बताइए, जवाब दीजिए, क्या ये बात clear है? Please answer me. Any issue? Okay. Now, once we have found the T mean, we can quickly find the power also. है ना? Power क्या हो जाएगा? So we know power is T mean into 2 pi NT by 60. We know T mean is equal to, power is T mean into 2, oh sorry, I have written N here, T here. Okay, so basically it is T mean into 2 pi N, so we have got the T mean here. Okay, so what is this T mean? It is 20,000 into 2 pi into 180 by 60. So I think if we do it, we'll be getting how much? How much we are getting from here? We are getting somewhere near 377 kilowatt. Right. Now I am more interested in the second part. First part I have done. Let's see if we can do the second part of it. Let's try. Let's try the second part. Now I think it is quite obvious to everyone that for the second part we require delta E max. Okay. Let's try it. Let us see if we can do it or not. Gautam, are you telling me delta E max beta? I think there is something, some difference is coming. It seems to be a little bit different from what I see here. Okay, you are saying moment of inertia, so it's very wrong. It's actually completely wrong. All right, I'll do it. So basically, we have found the T mean. Basically, we have found the T mean here, and then we have found the power. Okay. Now, in the previous cases that we have seen in the last score booster session, so when we draw this T theta diagram, okay, so this is your theta, this is your T. So whenever we are drawing this T theta diagram, so what we are having, so we have some T mean, and if the curve, let's suppose we don't know how this curve is going. So let me take some arbitrary curve. So let's suppose the curve is like this. I don't know how this curve will look like, and there is no need of plotting it also. Okay. So let's suppose the curve looks somewhat like this. Now, if the curve is looking somewhat like this, basically this is your delta E max. Please answer me yes or no. This is going to be your delta E max. Can you answer me yes or no on that? Bolo. Right. This is your delta E max now. Okay. Now, basically, if you want to find delta E max mathematically, so see, you are finding the area in these kind of a question. We were finding the area. Now, what is synonym to area? Mathematically? So that is integration. Right, that is integration. So the only way you can find it by integration, but you see that this is area above or maybe below the T mean line. So when we are integrating to find the delta E max, basically we need to integrate it like T minus T mean. We need to first of all integrate this. Now, students get confused, sir, why we are integrating T minus T mean? Because in the last session also we have quoted, and today also I want to repeat this, that fluctuations are the area above or below T mean line. So they have to be calculated from T mean. So that is why first of all T minus T mean. Now what is missing here? ये बताइए integrate करने के लिए what is missing here? For integration, what is missing? Here? Can you please tell me what is missing here? बताइए क्या missing क्या है? What is missing here? Can you please answer me? Wonderful. So definitely the limits are missing. Okay, we are missing out the limits. So what should be the limits here? Now for finding the limit, basically you are referring to, you want to find this A and you want to find this B. Yes or no? This is what we are want to find. Yes, Prasant. Okay, so we want to find this A and B. Okay. Now basically this A and B are the points, as we see, at which this curve is intersecting the T mean line. So basically where the two curves are intersecting, so at what point two curves intersect each other, to find that we need to equate their equation. So basically we need to equate this. Yes or no? We need to equate this. Now when we equate this, जब हम इसे equate करेंगे, so we are going to have, so what is the equation for T? It is 20,000 plus 9,500 sine 2 theta, and what we are having? Minus 5,700 cos 2 theta, and we need to equate it with 20,000. So basically we will left with tan 2 theta is equal to 5,700 divided by 9,500. Now from here, can you tell me what is the value of 2 theta? Can you tell me some values of 2 theta, please? Can you please tell me some values of 2 theta? बताइए. Can you tell me some values for 2 theta? So I think when you do it in your calculator, you are getting 31 degree, right? Right. What are we getting? Are we getting 30.96? Pranjali, you are telling me, no? Just one. Huh. 30.96, that means 31 only. And then we have to keep adding 180, 180 because sine cycle, tan cycle repeats in 180. So if I add 180 to it, so we'll be getting 211. Then further if I add 180, so we'll be getting, I think, 391 and so on. We can carry it up. We can carry it up. Yes or no, please answer me. Yes or no, please answer me. Okay. Okay, so basically now what will be this theta? So this is going to be 15.5. This is going to be, so 211 by 2, that is 105.5, and it is going to be, so 390. So we are getting 195.5, right? And so on. Okay, so at all these points, this curve will be intersecting the T mean line. But if you see, this goes beyond the range. It already crosses the cycle because our cycle is from 0 to pi, right? That is why some students say, sir, what is the need of this step? Some people ask me that what is the need of finding the cycle, because if we consider like we have chosen the right way and we have seen what is the extent of the cycle, but if you place 2 pi here, then only also you will be getting, then only also you will be getting 20,000 only. If you take 3 pi also, you will be getting 20,000 only. But the difference comes here that if you do not choose the right cycle, if let's suppose we have considered 2 pi, then we have to see the integration between 15.5 and 105.5 and then 105.5 to 195.5. Are you getting my point, beta? So don't do that. Okay. Okay, so where this curve is intersecting this, so we have got the A and B. जब हमें A और B अब मिल गया. Okay, so we can put the values here. Don't forget to change it into radian because the rest of the thing you are putting in SI units. Okay, and this is 105.5 into pi upon 180. Okay, now someone would say, sir, these are the trigonometric ratio. If we put in degree also, the answer will be same. But in some case, it may get different when there is some constant value also. So always have this habit that whenever you are dealing with SI units and you have to put the angle, you put it in radian. Are you getting my point, beta? Are you getting my point now? I hope all of us can integrate it between these limits, and when we integrate it, we will be getting 11078 Newton meter. Is it fine to everyone? Please answer me. 11078 Newton meter. Are we getting the same or not? Please answer me. Yes or no? Okay. Now once we have this delta E, so this is your delta E max, and we can now do it like this: I omega square CS. Okay, so this is 11078. I we have to find, so it is 2 pi 180 by 60 whole of a square, and CS I think is given to be 1%, so that is 0.01. So from here, when you find this I, I think you will be getting 3121 kg meter square. Now please tell me if it is clear to everyone or not. Please answer me. जवाब दीजिए. जवाब दीजिए. Please answer me. Is it clear? Now can we try with the last part? Any doubt in this particular part? Second, no, none of you were able to answer it correctly. I hope this is clear to everyone now. Let us see if we can do it. What is the answer to the third part? Yeah, Pranjali seems to be correct. Now, in the last part, what they are asking you to do, so they are asking you to find the angular acceleration of the flywheel when the crank has turned through 45 degree from the IDC. Now, what does the mean of this question? So when the crank is at 45 degree position, that means the theta is at 45 degree, you will have to find the angular acceleration. Okay. Okay, so angular acceleration, why there would be some angular acceleration to your crank? Because there will be some excess torque. Okay, and we very well know that torque refers to, torque is also I into alpha. Okay, I think we all understand this. So we must have known this. So whatever excess torque we have, excess torque means more than the mean torque. Okay, more than the mean torque. So whatever excess torque we are having, so by the rule of second law of Newton, we have this excess torque must be equal to I into alpha. So what is this excess torque? T minus T mean. T minus T mean. Okay, so we'll have to place theta is equal to 45 degree here. Okay, so what is this T minus T mean? So we have 9500 sine 2 theta. So that is sine 2 into 45, right? Minus 5700 cos 2 theta, that is cos 90, that is cos 90 is equal to I, we already have calculated 3121 and into alpha. Now I think from this equation we can very easily find the value of alpha, and when will you be finding it? You will be getting 3.044 radian per second square. Is it clear? Please answer me yes or no. Clear है ये बात? बताइए. Is it clear? Please answer me. So this was the second variation. Sorry, this was the third variation of the question of flywheel. Now, can I say to you that this is also clear? You will be able to deal with it when your function, when your torque is given as a function of theta. Will you be able to deal with it? Please answer me. Please answer me yes or no. Understood, I think, everything. Now coming to the fourth type. Okay. So till now they haven't asked this in the GATE examination, but in ESC examinations, etc., this question is getting asked in abundance. So basically for multi-cylinder engine. Okay, so we have some multi-cylinder engines as well. So for a multi-cylinder engine, if you want to calculate, so the question would look like this. The question would look like this. Okay. Okay, so you will have to find the maximum fluctuation of energy. So can you please attempt it? I'll just give you some more data here, because I think it seems some data is missing already. Just one moment, huh? So vertical scale is given, horizontal scale is. So I hope once you find this maximum fluctuation of energy, whatever else is asked, you will also be able to find it. So it is given horizontal scale 1 mm is equal to 3 degree. Okay, can you guys please try this question? How to do it? Now in multi-cylinder engine, beta, in multi-cylinder engine, you do not have to see the maximum fluctuation of energy directly. Okay, you will have to follow some process. Okay, हमें एक process follow करना पड़ता है. No, I want you to try this first, then I'll do it. Let's see how many of us can do it by yourself. Let's see how is our preparation. Let's do it, beta. So after this question, we shall be starting with the vibration part. हम vibration शुरू करेंगे after this question. That's right. So you will have to tell me maximum fluctuation of energy. Let's see how many of us can do it. Now, if you see this kind of a question, you will see that there are many areas above and below the T-mean line, and this is very much directly looking different to the one we have seen earlier. Okay. In the first time where T theta diagram of a single engine is given, you have seen that also, right? You have seen that also, right? And you have seen the one in which the torque is given as a function of theta. Both the questions are very, very different from it. Okay. Both the questions are very, very different from it. It will directly, when you see this kind of a question, you can directly see, you can directly judge. Very good, Pranjali, you have given the correct answer. You can directly see that how this question is different from the previous one. Okay. Now please do it. So I just have got only one answer till now. All right. So how we can do it? Okay. So I hope all of us understand that when we are saying that the maximum fluctuation of energy, so the maximum fluctuation of energy is maximum energy minus minimum energy. Can we write this way also? Maximum fluctuation of energy is E max minus E min. Is it fine? Please answer me. Is it fine? Okay. Now, from this diagram, if we can somehow find the E max and E min will be good. Okay. So, how to find it? Now, what we have to do, we'll have to start writing the energies. We'll have to start writing the energy from, so we can write it like this. So, energies at A. Okay, so let's suppose the energy at point A is E. We have considered a value that is E. Okay, so let's suppose energy at A is E. So what is the energy at B? So we have to do it like this. Energy at B is, so you see that it is going, the area is above the T mean line. So what can be said? We can say that it is E plus 52. Now what is the energy at C? So we can write E plus 52. Now you can see to see the area is downward below the T mean line. So we can subtract 124. So it is minus 124, right? Similarly, when we do it when we calculate, so we will be getting E minus 72. Okay. Now at D point you will have E minus 72, E minus 72. Okay. And this is going to be 92. So plus 92, so that is going to be E plus 20. I hope it is clear to everyone. Okay. Now similarly we can move forward. So we have D, then to point E. So energy at point E is E plus 20. Now to go to point E we have 140, that is minus 140. So we will be getting E minus 120. Similarly we can move to F. Okay, so at F it is going to be E minus 120, E minus 120 and plus 85. Okay, so what we'll be getting? We'll be getting E minus 35. Okay, E minus 35. Now G, at G, it is going to be So at G, it is going to be E minus 35, and we have this as 72, that is minus only. So E minus 35 minus 72. I think we'll be getting E minus 107. Now at the last point, that is H, it is going to be E minus 107 plus 107, that is E. Okay, so in this kind of a question, so it's very simple, no? It is very, very simple, right? Arey bolo na yaar, how we have done it. Now at the last point in this kind of a question, always you must get the same value at what you have it started with. जहां से स्टार्ट किया था सबसे पहले ई माना था, लास्ट में भी ई आना चाहिए, क्योंकि फ्लाईव्हील का फंक्शन कैसा होता है, हाउ अ फ्लाईव्हील वर्क्स. सो फ्लाईव्हील स्टोर्स द एनर्जी and then delivers it. So whatever energy is stored, that is only going to get delivered. Okay, so energy stored is always equal to the energy delivered when we are using the flywheel. Okay, when we are using this flywheel. So we are having all this like this, we are having all this. Now if we see, so all of it, if we see, so this is the maximum one, na? E plus 52, I think very clearly it is the maximum one, and this is the minimum one, right? Please answer me yes or no. Okay, so from here we can observe, that this is the maximum, this is the minimum. Yes or no, please answer me. Jawab dijiye. This is maximum, this is minimum. Okay, so the delta E max will be so E max is E plus 52 minus E minus 120. Okay, E minus 120, so it is going to be 172 mm square. This is going to be 172 mm square. Is it fine, beta? Please answer me. Okay, now we have to convert it. We have to convert it into, so what is the general unit of Emax? So we have to convert it into Newton meter. Now for that we are given with the scale. So this is 603 degrees. So always remember, so when we have to convert, so we have to convert the vertical and horizontal one. So that is 600 Newton meter and 3 degrees. So don't forget to change it into radian. Okay, so when you do it, you will be getting 5404 Newton meter. Now please tell me if it is clear to everyone. सबको clear है कि नहीं clear है, जवाब दीजिए. Please answer me if it is clear to everyone or not. जवाब दीजिए. Please answer me if it is clear to everyone or not. So now I think we have seen almost all the types of flywheel question. Okay. So other than this, you can see the punching press case also by your own. Okay. But I think for a score booster, I think this was the most important thing for the from the flywheel point of view. Right? Clear to everyone? Okay. Now shall we move to the vibration part? Vibration पे चलें? Yes or no? Wonderful. Okay. So, if I speak that which is the most important topic in this particular subject, so this is the most important. So normally every year without any deviation, this particular topic is getting asked in 2 to 4 marks. 2 से 4 नंबर में ये टॉपिक आप लोगों का पूछ लिया जाता है, ठीक है. सो लगभग 2 to 4 marks. Okay, so perhaps the most important topic in theory of machine. Okay, and like every year there is a question of vibration. Okay, so this particular topic is divided into 3 parts. One is the natural vibration. Okay, okay. The second one is damped natural vibration. And the last one is the forced damped vibration system. The forced damped vibration system. So we have the natural vibration, damped natural vibration, and forced damped vibration system. So these are the three kind of systems. These are the three kinds of system. Okay, here. So in the first system, let's first talk about the natural vibration. Let us first talk about the natural vibration. Okay. So basically, there are several methods. Okay, to find the natural vibration, or to there are several methods to solve for the natural vibration question. Okay, so first of all, very simple method. So let's suppose, so if we have a spring and we have a mass attached to it, so if I consider this spring to be massless, अगर spring को massless पकड़ लें, तो ये एक basic natural vibration system की representation होती है. Okay, so what we are interested in, so whenever we say vibration, basically vibration, whenever I say vibration, so you can imagine something. Okay, it's a to and fro periodic motion. Yes or no? Whenever we name, whenever I say this name vibration, it is basically to and fro periodic motion, right? Now, whenever some motion is to and fro periodic, whenever some motion is to and fro periodic, whenever some motion is to and fro periodic, okay, definitely it is having some frequency. So what we are interested in here, we are mostly interested, most of the question of the vibration, you will see that they are asking you the frequency. Okay, so basically this is the governing equation. Okay, x double dot plus omega n square x is equal to 0. Okay, so in case of natural vibration, you will have to make an equation like this in some question. Okay, you may have to make an equation like this in some particular questions. Okay, and then you will have to relate or compare. Okay, so what is this omega n? So this is the standard formula. This is the standard formula. So this is going to be S by M, where S is the stiffness of a spring. Okay, so always remember, if you want to find this omega n in radian per second, अगर आपको omega n radian per second में चाहिए, so S is the stiffness of a spring and you will have to put it in Newton per meter. आपको किस में रखना पड़ेगा? Newton per meter में रखना पड़ेगा. And this mass you shall have to put it in kg. आपको इसको kg में रखना पड़ेगा. Is it fine, beta? Please answer me. Okay. So if very simply, if I give you the stiffness and the mass, definitely you can find me the value of omega n. Okay. Now some cases happens to be, in some cases what happens, my dear, okay, so they will give you combination of a spring, maybe in series or maybe in parallel. Now I want you to try this question. Okay, so you can't do it right now. Just one moment, we haven't reached to this point. Okay, can you please try this one? Let's try this one. Let's see if we can do with this is series and parallel connection. Let's see how much we know it, because I am assuming that already we must have some information about it. Let's try this one. Let's see if we can answer it or not. So this is what we call it as series and parallel connection. Okay. So basically, what shall be your approach? So ultimately, we have to find this omega n, natural frequency in radian per second. So basically, it is going to be stiffness upon m. Okay. So we see that the m is clearly mentioned here. We can see that m is clearly mentioned. No problem with the m here. The only problem lies here with the s. So basically, these are the combination of a spring. These are the combination of a spring. So we have to find equivalent s. Okay, and we have to put it there. Let's see if we can do it or not. Let's see how much of us knows how to find the equivalent stiffness. Definitely when I'll be solving, I'll be telling you. Dheeraj, I have given some answer. Okay. Now, how we can deal with this kind of a question? So basically, all we are required to find is the equivalent stiffness. So when the springs are in series, okay, when the springs are in series, okay, they look like this. Okay, one after other. Okay, then so if it is S1, it is S2, this is S3. So how you can find your equivalent stiffness? You can find it like this: 1 by S1 plus 1 by S2 plus 1 by S3. So this is how you can find the S. Okay, this is how you can find your S, right, beta? Any issue? I hope there must not be any issue here. Okay. Similarly, if the springs are in parallel, if springs are in parallel, okay, so it will look like this. Okay, let's suppose this is M, this is S1, this is S2, or we can also represent it like this. So some people think that this is your series connection. No, this is also parallel connection. Are you getting my point? This is how we can represent the parallel connection again. So basically, what is the equivalent stiffness? It is going to be S1 plus S2. Is it fine to everyone? Please answer me. Is it okay to everyone? बताइए, ये ठीक बात है? इसमें कोई दिक्कत तो नहीं है? Right? Now we can try solving this question. No? So first of all, I'll have to find the equivalent stiffness here. So 1 by S is equal to 1 by 10 plus 1 by 15 plus 1 by 5. So what is the S we are getting from here? What is the S we are getting from here? Can anybody please tell me that? What is the stiffness we are getting from this? Anyone? So we are getting, I think S is equal to 2.72 kilonewton per meter. Please have a check. Okay, okay. Somewhere near this. Have I found it correctly? Okay, so it is coming out to be 2.72 kilonewton per meter. So we can find from here the omega n1 na. So basically it is, do not forget to multiply 10 to the power 3. Okay, so m is not given, so this is going to be m. Now for here, now all these three springs are in parallel only. All these, so my voice is low. Please check the sound. Are you guys getting my voice very low? Sadik is telling me that my voice is low. What about the rest of you? Are you getting my voice fine? My voice is fine, or is it low? Can you please reply me on that? Okay, today it is bit low. Okay, okay. So just after this question, I'll get a check. Okay, okay, okay. No, just give me one moment. I got the point. So there must be some technical issue. I'll look into it. Just once. Just give me after this question. After this question. Okay. Okay. Huh. Okay, okay. Because I'm using a mic, no. It is not about that how loud I am speaking. Okay, I'll get it done. Just 1 minute after this question. Okay, so why you guys were not telling me by this time? Okay, in the starting, or you could tell me that. Now in the second case, we can understand this S1, S2, and S3. Dheeraj, this is something you must tell me from the very starting. No, why you were taking this pain? Okay, so all these three springs, all these three springs are in parallel. So when they are in parallel, we can find the stiffness by simply adding them up. Okay, so this is going to be 30 kilonewton per meter. This is going to be 30 kilonewton per meter. Okay, they all are in parallel. Sometimes people think that these two are in parallel, then this is in series. No, this is not like that. So from here we can say, what we can say, that omega n2 is equal to root over 30 into 10 to the power 3 by mass m. Now definitely we can take the ratio of omega n1 and omega n2 and can get this data. Okay. Okay. Okay, Dheeraj. Okay. No worries. I'll fix it. Just 1 minute. Okay. So this kind of a problem in which series or parallel thing is given to you, will that be okay? You will be able to do with that? Yes or no? Please answer me. Okay. So now we are going to have a break of 5 minutes. I'll fix the voice. Okay. I'll fix the voice and then we'll continue. Okay. And from the next session, do tell me so when I start the session, I always ask you guys, na, whether you can hear me. So please do tell me if there is anything, because obviously I can't hear me. Okay. So I'm just, I can't hear me on the YouTube. No. Are you getting my point? Okay. I'm just seeing your chat. I can't see me also. Okay. So if anything wrong, always do tell me. So we are going to have a break for 5 minutes. In that time, I'll fix this voice also. Okay. All right. So guys, please tell me if you can now hear me well. Okay, so there was some problem before. Okay, so now can you hear me properly? Can you hear me properly now? Okay. Can you guys hear me now? Please answer me. Is there still any problem? Now my voice is now good enough. अरे बोलो ना भाई. Sadik. Is it still low? Okay. Just 1 second. Where is the problem? Is it still low? Okay. So this is still low. Okay. Okay. Just give me one more moment, huh? I'm putting it on the break, and just within 1 minute I'll be back, huh? All right. Yeah. So the team is looking into the matter, guys. The technical team is looking into the matter. There might be some technical issue. Okay. So they are fixing it. They are fixing it. So meanwhile, I think you can hear me, no? The live students. Can you hear me? My voice is low, or is it completely? Am I completely unaudible? Okay. Okay. So we can continue with the session. Meanwhile, the technical team is looking into it. Okay, and do let me know when the voice comes to be fine. Okay, do let me know. Okay, okay, okay. So it is low only, but you can manage it with it for some time being, right? So let's continue the session. Let's continue with the session. Let's continue with the session, and the technical team is looking into it. Okay. So so this is the first type of question they get asked to us. They ask to us. This is the very first type of question. Uh, this is the so now voice is fine. The low thing is low. The low voice thing is now okay. Is that okay now? Because the technical team is looking into it, so we are trying to sort it out. Okay, just let me know. Just let me know when the things get better. Okay, so that I can ask the technical team to. All right. Okay, very well. Okay. 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 So it's low but audible. Okay. Okay. So let's start with the next question. Huh? Now, so this is a question. This is one more question that we are supposed to do. So this is the first type of question where we deal with the spring connections, like it could be parallel connection, it could be series connection, or it may be combination of both parallel and series connection. Are you getting my point? Now this is the second type of question in which we can have the vibrations in the form of oscillation, like the angular oscillations. Are you getting my point? Okay, can we please try doing it? Let's start doing this question. Let's see if we can do it. Let us see if we can do it. Let's see if we can do it. Let's see how we can do it, beta. Let us see how we can do it. So you can consider this rod to be of uniformly distributed mass. Okay, don't consider it massless. So we have two springs, and these questions you will see are coming in abundance. These questions you see are coming in abundance. Okay. These questions are coming in abundance. If you see the previous year gate questions, you will see this kind of a question in which we are supposed to give the angular disturbance initially, in which we are going to give the angular displacement initially. They are getting asked in abundance. Let's see if we can solve it. Let's try to solve it. Any answer? Any answer? How we can solve these kind of a questions? Any answer to this question? Okay, I'll do it. Shall I do it? I think we must be able to do it if we are preparing for the gate examination. I hope we must have to do it. Okay, so mass you can consider. So you can consider the mass of this complete rod as 10 kg. All right, you can consider it as 10 kg. All right, no worries. This is the distributed mass. So how we can do it? How we can do it? So first of all, see guys, see. So whenever we have, so in the previous case, now please observe, we have started with this now. We have started with this. Okay. Now in this case, my dear, in this case, we are giving it the vibration like this. We are giving it a vibration like this. We are pulling down the mass. So let's suppose we have a spring and a mass system with us. So in this system, we call it as linear vibration, all longitudinal vibration. So we bring it down, we leave it. So it vibrates like this, somewhat like this, to and fro periodic motion. Now in the case of this torsional vibration, okay, we are looking forward for, so we are having something like this. Let's suppose this is your mass. Okay, now we are going to give it some angular displacement. Now we are going to give it some angular displacement. So we have a mass here, so we are going to give it some angular displacement like this. We are going to give it some angular displacement like this and leave it. Okay, so it will go like this. Okay, this will be the way it vibrates. Okay, so basically when we have a hinge, the basic understanding is when we have the hinge, definitely about the hinge, the vibration would be in the form of like this, angular vibration. So the first step that we must do is that we must be giving this, okay. So the first thing that we must do, that we must be giving it some angular displacement. Okay, and then we can see what are the torques here. That is why it is also called as the torque method. So in this case, we have to give it some displacement. Let's say we have given it a displacement of theta. हमने इसको theta displace कर दिया, ठीक है? We can give it displacement on either side. Okay, in this I have given it displacement in this side. You may give it in opposite side also. Okay, so in this case we have given the displacement in the anti-clockwise sense. Okay, you can give the displacement in clockwise sense also. That is nothing to worry about. You will be getting the same answer. Okay, now see, in this subject or in any subject, whenever we have some hinge, what is to be done about the hinge? In any subject, whenever you see, whether it is a strength or material, fluid mechanics, any subject, whenever you see a hinge in your problem, okay, we always have to take the moment about that hinge. We always have to take the moment about that hinge. So what are the forces here in picture? What are the forces here in picture? So we are having a mg here. Okay, okay, this rod mass center, let's suppose uniformly distributed, as I said. So its mass center will be exactly coinciding with the geometrical center. So this is going to be mg. Now you see this spring is getting compressed. This spring is getting deformed and it is getting compressed. So when it is getting compressed, it must be giving the force in this direction. Okay, due to the stiffness of the spring, the force that is acting, the stiffness of the spring, the force that is acting is opposite to, the direction of the displacement, So this is going to be, so how much this spring would displace by? Okay, so this is 0.5. Now we know, so if I move something with a very small angle and this is theta, and this is L, so I hope that all of us knows that this is going to be L into theta. For a small trigonometric angle, we can do this. Okay, so now this spring will be compressed by how much? It is going to be compressed by, so this is 0.5, so it is going to be 0.5 into theta. And what is this force? So force is stiffness into displacement. So let's suppose this is 3. So let's write it 3 for now. Okay, okay, so this is going to be okay, so let's write it 3 only, no worries. Okay, now this spring is stretched, this bottom spring is stretched, so what will be the direction of force? due to the stiffness of the spring, the direction of the force is always opposite to the displacement. So this spring is getting stretched, right? This spring is getting stretched. Okay, so the force will be in opposite direction. And how much this force would be? So for a small trigonometric angle, what will be the displacement of it? It is going to be 0.75 into theta. It is going to be 0.75 into theta, and the stiffness of this spring is 2 kilonewton per meter. So this would be the force here. This would be the force here. Yes. Now we have these three forces. We have these three forces, and we have to take the moment of these three forces about the hinge. So if I take it like this, so we have 2 kilonewton meter. So for kilonewton, we can put 10 to the power 3 into 0.75. Okay, so this is your force. Okay, so what is to be multiplied with the force to make it? What is to be multiplied with the force to make it the moment? So definitely distance is to be multiplied. So this is the direction of the force. And what is the perpendicular distance from the hinge? It is 0.75. It is 0.75. Okay. Okay. And this is going to be your clockwise moment. This is your clockwise moment about the hinge. Okay. Now, if you see this force, so what is the force? So it is 3 into 10 to the power 3. Okay. Into, okay, so we have to multiply theta also, na? It is theta also. Okay, it is theta also. So we are multiplying theta. 3 into 10 to the power 3 into 0.5 into theta. So this is your force. This is your force. Okay, and we have to multiply it with the perpendicular distance. We have to multiply it with the perpendicular distance. So what is the perpendicular distance here? It is 0.5. It is 0.5, right? Okay, now what is this mg? Okay, so we have this mg. Now, what is the perpendicular distance of this mg from the hinge? So this is the perpendicular distance, beta. This is the perpendicular distance. So this is going to be mg into. So this whole length is 1 meter. This whole length is 1 meter. Okay, this whole length is 1 meter. So mg is L by 2, that is 1, that is 0.5. So basically this force is at the same point. This spring is also at 0.5. So that is on the center only. That doesn't matter. We have to follow the procedure. So 0.5 into theta. Is it fine? Is it fine? Please answer me. Okay. So due to this spring force, bottom spring force, due to this bottom spring force, we are having this much force, this much force. Due to this spring, we are having this much force. And the moment about the hinge, the mg is giving us this much moment. Okay, this much moment. And we have one more thing here. So this is the representation of torsional spring. Okay, torsional spring. So this torsional spring, what does it do? So basically this is your torsional stiffness. This is your torsional stiffness. Okay, this is what? This is your torsional stiffness. Are you getting my point, beta? So now this rod is moving in anti-clockwise direction. So this torsional stiffness will give a torsion which will be resisting this motion, this anti-clockwise movement. So this torsional stiffness will give the torque directly or the moment directly to resist it. So this is moving in anti-clock. So definitely this is going to give you, so what is the torsional stiffness? It is 1 kilonewton per meter. 1 kilonewton meter per radian. Okay, so we have to multiply it with theta. So this is also clockwise. This is also clockwise. So this is also clockwise. So when we give it a oscillation, when we give it a small displacement, when this bar is given a small displacement by theta, when this bar is given a small displacement by theta, we are having this much moments acting about the hinge. We are getting this much moments acting about the hinge. Now what we can do? We can sum them up. Okay. So did you understand it, or is it got too complicated with the value? So let me do this way. Just one more moment. I think this got too much complicated with the calculation. So let me take some data. Okay, for explanation. So let's suppose this is S1. Okay, this data will do. Okay, so see, let me try to simplify it a bit. Okay, so let's suppose this is A. Okay, let's suppose this is B. Okay, we are given with A and B, and let's suppose this is L. The whole length of it is L. Okay, so whenever you see a question like this in which hinge is applied, first thing, the first step, you can give it in oscillation in either of the direction. You can give it in here, you can give it here, or you can give it on the other side. Okay, so when you displace it by theta, okay, then you will have to see with the displacement of theta, when we displace this rod by theta, what are the moments that are coming about the hinge? So what will be the moment? So this spring is stretched, so this is the direction of force, and what will be the force? It will be stiffness of the spring into the displacement of this spring. So this is A, this spring will displace by A theta. Okay. Similarly, this is getting compressed, so the force will be opposite to the direction of this displacement. So this is going to be S2 into B theta. This is going to be S2 into B theta. Okay, and this is your mg. Okay, this is your weight which is acting at the center. Okay, now what we can do, we can take the moment. Now to take the moment, we have to multiply the force with the perpendicular distance. So what is the perpendicular distance of this force? S1 A theta to the hinge. So basically it is the perpendicular distance of this force to the hinge is A only. So this is S1 A square theta, and you see this clockwise. So if it is a vibration problem, all the moments will come in the same direction only, whether it is clockwise or anti-clockwise. If you want to try it, you give it a displacement in the opposite direction, then you will see that all the moments that are coming here will be coming in the anti-clock direction. Are you getting my point? Are you getting my point? So this is going to be S2B square theta. Okay. This is also clockwise, and this is mg, and this distance is, so if this whole is L, this distance is L by 2 theta. This distance is L by 2 theta. So we are going to get mg L by 2 theta, mg L by 2 theta about the hinge, and we are going to have it, we are going to give it a clockwise moment. Right? So how these moments are clear, I think. No problem at all. Now, if we place a spring here, if we place a torsional spring here also like this, okay, and let's suppose it is having a stiffness of S theta, okay, stiffness of S theta. I hope you are getting my point. Now, since this rod is displaced in the anti-clockwise direction, okay, so definitely this is due to the stiffness of this torsional spring. This torsional spring will try to bring it to the original position. That means it will giving it a torque which is clockwise in nature. So from the torsional stiffness, how we can find the moment. So we can multiply this torsional stiffness with the theta, and definitely it is also going to be clockwise. So all you have to do, you will have to just add them up. Okay, so when you add them, so you will be getting, let's see what we are getting. So we are getting S1A square plus S2B square plus mg L by 2 plus mg L by 2 plus S theta into theta. So these are all the moments. These are all the moments that we see here about the hinge when we displace this rod. Okay, now we have to apply the D'Alembert principle or the Newton's second law of motion. So I'll prefer to apply the D'Alembert principle here. So what we have to do, simply we have to equate it zero. We have to equate it to zero by adding the inertia force. So we know in the angular system, the inertia force is I into alpha. Inertia force is I into alpha, right? Okay, where alpha is angular acceleration. So now can we say, so alpha is when we differentiate this theta one time with respect to time, we get omega. That is the angular velocity. And when we differentiate this angular velocity with respect to time, you are going to get the angular acceleration. So theta double dot means that theta differentiated twice, okay, with respect to time. So this is going to be I theta double dot. Now what we have to do, we have to compare it with our basic equation. Okay, so what was the basic equation? omega n x double dot omega n square x is equal to 0. So instead of x, we in angular system we replace the x with the theta. We replace the x with the theta. So from here we can get our omega n, that is s1a square plus s2b square plus mg L by 2 plus s theta divided by I. So this is going to be your omega n. Is it clear, everyone? Beta? Now sometimes the student make mistake in this I. So whenever you are using torque method, don't confuse it with your energy method. We have one more method that is known as energy method. So in energy method also we sometimes use this I thing. Okay. There the I is different. Here in the torque method, always take the I about the hinge. Okay. Now if we have a rod like this, okay, so we want to find this I naught. Okay, we want to have this I naught. So what will be this I naught? So if I say this is uniformly distributed, so we have G at the center. So what is this G? What is the moment of inertia about G? So this is your standard formula. If the length of this rod is L and the mass of this rod is M. So this is the standard formula of getting this G, that is Ig is equal to ml square by 12. But what do you want? You want the moment of inertia about the hinge. So you have to apply the parallel axis theorem. So it is going to be Ig plus M, distance between the point about which you want to find the moment of inertia and the centroid or center of gravity. The same you may use in the finding area moment of inertia also, right? Because so we are going to have I naught is equal to Ig plus MOG square. So I naught, it is going to be ml square by 12 plus M, so just OG is L by 2 whole of a square. So it will come out to be ml square by 3. Don't memorize. Okay, you can apply the parallel axis theorem and can find. All right. Now please tell me. So the question I have given like this. This was the question, right? This was the question. So in this question, I think all of us can do. We all just have to place the values, taking care of the unit, and can get the answer. Now I want you to do. Now first tell me, is this process clear to everyone? How we have done this kind of question? Okay. Please answer me yes or no. Those who are live. Jawab do bhai. Is this clear? अरे बोलो ना भैया. Very good. So my voice is improved or it is the same only? Is it improved now? Please respond to that also. Okay, let's do one question or one more question. Okay. The mass of this rod is 10 kg. Let's try it. So voice, okay, it is same only, no? Okay, same only. Okay, no worries. Okay, so like, I think the some technical issue is there, so we have to carry on with this only. Chalo. Let's do it, beta. Let's do it. Let's rest of you. Let's see if rest of us, all of us can do it. You have to find omega n. You have to find omega n here. Let's see how we can do it. Any answers? Any answers? Okay, so Gautam have given some answer. What about the rest of you? So when we see this question, I think we realize that this is a question of vibration, right? जब हम ये क्वेश्चन देखते हैं तो हमको ये सीधा रियलाइज होता है कि ये क्वेश्चन हमारा वाइब्रेशन का है, right? Now the second thing that we observe, okay, there is a hinge. So when this is a hinge there, when we have a hinge there, we need to do it by the torque method. हमें इसे एक angular displacement देना पड़ेगा. We have to give it a angular displacement. Okay, so let me make a equivalent system. है ना, इसको थोड़ा सा सिंपली बना लेते हैं. So we have a spring here. Okay, we have a hinge here. Okay, the distance is L by 6, right? Okay, the distance is L by 6, it is going to be 2L by 3. Okay, so we are having it as 2L by 3, and this is your, okay, we have one more spring here. And in the very end also, we are having one spring. In the very end also, we are having some spring. Okay, so what are the stiffnesses given to us? This is 10, 5 and 10. So this is 10 kilonewton per meter. Okay, this is also 10 kilonewton per meter. And this is 5 kilonewton per meter. So this is the arrangement. and this is going to be L by 6, right? So this is your arrangement here. So I have got only one answer till now. What about the rest of you? So now once we observe, this is a question of torsional vibration or torque method. What we can do, we can give it a theta. We can give it a displacement. So this is theta, this is also theta. And as explained, you can give it the displacement in the opposite direction also if you want. It is not necessary that you give in the same direction. You can do like this also. No worries. Okay. So Shred is giving me also some answer. Let's see. So now definitely the direction of the force on this spring would be this, right? Okay, every answer is different only. I have got 3 answers, all 3 answers are different. This is going to be in this direction because it is coming downward, and this is also going to be in this direction. First, this direction thing I hope is clear to everyone, how I am choosing the directions here. Okay, now this is going to be 10 into L by 6 theta, right? This is the force, stiffness of a spring into this distance into theta, into the displacement. Okay, this is your going to be 5 into, so what is this, 2L by 3 into theta, and this is going to be, so this is going to be 10 into 2L by 3 plus L by 6. So it is going to be 5L by 6, right? 5L by 6 theta. Yes or no? These are the forces. Is it fine to everyone? Please answer me. Is it fine to everyone? Arey bolo na yaar. Is it clear till now how we have seen the forces? Arey bolo na yaar. Right. Okay. Now remember, the previous question was of the, in this question, this is a vertical case. Okay. Now, what is the difference between horizontal and vertical case? So, in horizontal, never take the mg torque. Okay. We do not have to take the mg torque. Why is it so? Why is it so? Because if it is maintaining its equilibrium condition, so the mg torque is somewhat balanced by the initial displacements, the forces due to initial displacements of the spring, right? So when you see a figure like this, so this can maintain this original condition. So if you are seeing this figure, let's suppose we are having this figure. So how it can maintain its condition? How it can maintain its condition? Definitely there will be some mg. Okay, when you see it without you displacing it, please try to understand this. Let's suppose we have not given any displacement. Till we have not given any displacement, this particular system will maintain this condition as you are seeing it right now. How it can maintain its condition when there is some mg torque? There will be some mg, na? Okay, so this mg moment will be balanced by the moment caused due to the initial displacements of the spring by the virtue of this mg. So mg torque is balanced already. Okay, mg torque is balanced. This mg torque is balanced already. Are you getting my point? This mg torque is balanced already. Okay, understood? Okay, so in basically what is the point? Whenever you see a horizontal system, you do not have to take the mg torque. That's it. Okay, now we have all the forces then. Okay, let's do the thing that we do always. So we are having 10 into 10 to the power 3 L by 6 whole of a square, right? L by 6 whole of a square. Okay, L by 6 whole of a square. Then we are having this 5 into, so that is going to be 5 into 10 to the power 3 into 12 by 3 whole of a square. Okay, plus, so all are giving the moment in the same anti-clockwise direction. It is always the case. Whenever you see a case of vibration, all the moments will be in the same direction only. Okay, so we are having it as 10 into 10 to the power 3 into 5L by 6 whole of a square and all multiplied to theta. All multiplied to theta. And when we have to put it equal to 0, I'll have to add one thing, that is I theta double dot, that is the force of inertia. That is the force of inertia, right? Now the question is, what is this I? So always remember, we have to take this I about O point. So we'll have to do like this, ml by 12, ml square by 12. That is the moment of inertia about the G. That is the moment of inertia about the G. So we want it about the O. Okay. So what is the whole length here? What is the whole length here? So we have L by 6 plus L by 6 plus 2L by 3. So L by 6 plus L by 6, that is L by 3. L by 3 plus 2L by 3, that is L. So the whole length of this bar is L only. Okay, so that means this is L by 2. This is L by 2. And we are interested to find this OG. So this is going to be L by 2 minus L by 6, right? L by 2 minus L by 6. So we can apply the theorem of parallel axis. So we can say M L by 2 minus L by 6 whole of a square. So this way we can find the I naught. This way we can find the I naught. And let's suppose this term will come out to be X. Let's suppose, so L square will come here. L square will come here. Will the middle moment, why it would carry the negative sign, beta? Shred, what kind of a moment this is giving? This one. This, let's focus on this one. About the hinge, is it given an it is giving an anti-clockwise moment or not? Please answer me yes or no. This very first one. This force is giving anti-clockwise moment, right? About the hinge, this is also giving an anti-clockwise moment, right? This one is also giving an anti-clockwise moment, right? And this one is also giving an anti-clockwise moment, right? Okay, so all the moments are anti-clockwise in direction. Okay, so when all the moments are in same direction and you ultimately have to put it equal to 0, you ultimately have to put it equal to 0. So you can choose whether you are going to take the positive sign or negative sign. If you want to take negative, you will have to take the negative to everything. Okay, and then it will be, when you are putting it to be equal to 0, that minus will have no meaning. So why unnecessary complicate, right? I think you are thinking that, sir, since the moment is anti-clockwise, we have to take negative. These things do not hold in vibration or anywhere when you are equating it to 0. Like whenever you are for example, if you see in the strength of material, okay, whenever we are finding the reaction, it never matter that what sign convention you consider clockwise to be positive or anti-clockwise to be positive, that doesn't matter. So here we are dealing, actually what we are doing, we are establishing that dynamic equilibrium. Are you getting my point? So this negative thing has no meaning, right? So now can we find all this thing? Can we find, so let's suppose if this is X, so what will be this omega n? So whatever will come here, you can put it like this, X upon I naught, whatever you find from here, and you will be getting the answer, right? You will be getting the answer. So always this omega n, that what we are getting here, so we are getting it in radian per second. If you want to find in hertz, what has to be done? We have to divide it by 2 pi. Okay, I hope all of us are aware of it, right? All of us are aware of it. Now please tell me, will you be able to deal with this kind of questions? So you will see this kind of a question in abundance. Are you getting my point? You are going to see this kind of a question in abundance when you see GATE previous year question, and every year these questions are coming, right? So can we move ahead? Did you understand this type of problem in which hinge is given? Please answer me. The problems in which hinge is given. Wonderful. Now, till now we are talking about the natural vibration only. Now there is one more way to find, which is particularly useful in some sort of problems of some kind of problems. It is particularly very useful. So we call it as Rayleigh method. What we do call it? We call it as Rayleigh method. Okay. So what is this Rayleigh method? What is this Rayleigh method? Or sometimes we refer it to as static deflection method. Sometimes we refer it as static deflection method. Sometimes we do refer it as static deflection method. So what is this in this method? What we are going to do? So we are going to find omega n as root over G by delta, where delta refers to the static deflection due to some load. Okay, this delta refers to the static deflection due to some load. Now, if I ask you what is this, what is this? What I what is here I have made? Please answer me. What is this? Can you tell me what should I name this thing? Hmm? Please answer me. What shall I name it? Anyone? Anyone? Please tell me. What shall I name it? क्या नाम दूं भाई इसका? Ah, acha, Gautam, you remember this thing. Okay. So this is nothing. This is nothing. We cannot say anything. Dheeraj, you are saying cantilever. My dear, it will be cantilever only when the transverse load, transverse shear load or the moment is applied to it, my dear. If we apply a load like this, it wouldn't be a cantilever now. It will be called upon as a bar. Okay, so don't say like that unless the load is defined. Okay, try to understand it. This is very basic of the strength of material. So a beam is something over which the transverse shear load is applied or some moment is applied. Okay, shed, again it is not, now it is cantilever. Now it is cantilever. Now when I show you this figure, there must be some formula that will be jumping out of your mind if I ask you to find the deflection of this point B. If I ask you to find the deflection of this point B, if I ask you to find the deflection of this point B, what you will be saying? If I ask you the deflection of this point B, what you would be saying? Some formula would be coming out from, jumping out from your mind, and you would say that this deflection at B is WL cube by 3I. I hope all the aspirants of mechanical engineering must have memorized this. Yes or no? Now, sir, what is the relevance here? Now, if you say, if you have like a cantilever on which a load W is applied or simply supported beam on which center load is applied, all you have to do is to find the static deflection due to that load, and you can put it in the formula of omega n. You can put it in the formula of omega n. So, omega n is going to be root over G by delta. So, in this case, it is going to be W, and W we know is mg, right? If mass is attached upon 3 EI, where E is the Young's modulus and I is the moment of inertia again. Now, I want you to do this question. Let's try this one. So, you will have to find the natural frequency in hertz in this case. Please go for it. Let's see if we can do it or not. Let's see if we can do it or not. Can we please try this one? Any answer? Any answer? I think we can very simply do it. Any answer? Any answer, my dear? Any answer? Do we have any answer, beta? What's the problem? क्या problem है? सॉम याद नहीं है बिल्कुल. We see this kind of question in strength of material, no? Till now, no answer. How difficult is this? What is so difficult about this? All right, let me do it then. Okay, so when we see this question, so when we see a problem like a standard problem, it is from the deflection in strength of material. Are you getting my point? So whenever we see this kind of thing, we always have to do it. We always must do it with the Rayleigh method, that is omega n is equal to root g by delta. Now for that, you will first have to find the deflection, the static deflection of it. And why we are calling it static? So if we are not doing anything, this is going to be the static diagram. No, this is your you see this kind of problem in strength of material also. So what is the formula to find the deflection in this kind of a case? Okay, so basically, I thought you must be knowing this formula. This is a standard formula, no? This is W. If this hole is L, this is A, this is B. Okay, so what is the standard formula? It is WA square B square. It is WA square B square upon 3EIL. Right, this is the standard formula, no? This is the standard formula, no? Yes or no? Please answer me. Okay, should have given some answer. Let me check. No, your answer is not correct, beta. Okay, so this is going to be WA square B square upon 3I. So we can write this directly, we can do, no? So omega n, so G and G will be cancelled out, no? Because this is given in the mass. So we can write it as 1 upon M. A is what? 0.25. So it is 0.5 square, 0.25 square. Let me write it here. So I'll be writing it here. So this omega n is root over G by delta. So G will be cancelled out only. So we don't have to write the G. Okay. So it is going to be 1 upon mass, that is M. So M we can put, so what is this A? Acha, Gautam, no worries. So I am teaching it, no worries. Okay, don't worry. So M into 0.25. So you don't know any method to find the deflection, Gautam? No. Are formula you can derive it, na? If you can derive it by Castigliano theorem, you can derive it by area moment method, you can derive it by double deflection method. And as I know that sir must have taught you this, no? Yes or no? You can do it by area moment, Castigliano, any theorem you can apply, you can do it. Okay, so you know the basic theorems, na? Gautam, what you are talking about, beta? Hannah, this gate, in the gate examination, if this question come, would you say this? That I do not remember this formula. You know how to derive the formulas in the deflection. Na? There are so many cases you cannot be able to find. Morse method, any method you can apply, no? Morse method, Castigliano theorem, okay? Double integration, any method you can apply and solve. So this is going to be 0.25. There is actually no need of memorizing the formula. If you memorize, although but this is a standard formula, do memorize it. No, in the examination, we can't take all these risks. So this is a very standard case actually. So memorize it, no worries. Upon 3 EIL. So E is given 200 into 10 to the power 3 Newton per mm square. We have to take the deflection under the load. Always in the case of a static deflection, we have to take the deflection under the load at all the times, right? Okay. So we have the value of E. So it is 200 into 10 to the power 3 Newton per mm square. So you can put this E value. Remember to change it in meter. Okay, Newton per meter square, because as you are putting everything like that, and the diameter is 50 mm. So the diameter, so what is the moment of inertia of a circular cross section? What is the area moment of inertia? That is pi by 64 into 50. That is, change it also in meters. So this is going to be your omega n. Okay, but in this formula you are going to get in radian per second. Whatever you are going to get, you will be getting radian per second. Then you have to divide this by 2 pi to get it in hertz. Okay, so when you do it, you will be getting 49.85. You will be getting 49.85 hertz. Is it fine to you, beta? Please answer me. Is it fine to you? Please answer me. Bolna bhai. Is it fine to everyone? Please answer me. Okay, I hope you can take care of the calculations here. Right? Arre bolo na yaar. So this is static deflection method is clear, no? Is this a static deflection method clear to everyone? Okay, Shred, have you done the same way? Shred, have you done the same way? Or did you do anything differently? Did you do anything differently? Okay, Mehul. Okay, good. All right. Okay. So let's move to the next part. Okay. So this is in natural vibration. Okay. So let's complete. Let's try to do as much as we can. So the next one is pi by 64. So if it is a circle, Okay, so what is this area moment of inertia? Arey yaar, shred. Okay, this is W. Okay, I hope all of us have seen this formula. Just talking about the cantilever beam. Okay, just talking about the cantilever beam. So what is the deflection here? It is WL cube by 3I. What is the deflection here? WL cube by 3I. So what is this I? This I is area moment of inertia, and for circular cross section, this area moment of inertia is pi by 64 d to the power 4. No? Right? Yes or no? This is the standard formula. That is what I have used here. Right? For rectangular cross section, it is BD cube by 12. Do we know it or not? I think we must know it. Yes or no? Understood? Okay, can we move ahead? Can we now move ahead? Okay, let's move ahead then. So the next part is when we talk about the damped natural vibration. So now we are going to talk about the damped natural vibration. Right? The damped natural vibration. So in this damped natural vibration, there is one add-on, that is we are considering the friction also, okay, in the system. So any system practically must have the stiffness. Any system practically have some stiffness. So this is mass, and this is going to be your what? Damper. This is going to be your damper. So this is the representation. This damper is something. This damper is the representation of friction in the system. So this friction is also so. What is the meaning of a spring? So a spring is also resisting it, na? Whenever something is having some motion, this spring is also giving us some resistance in the form of stiffness that we have to overcome. Right, beta? Similarly, this friction is also giving you some sort of the resistance to motion, right? So this damper is just the representation of friction in the system. This damper is the representation of friction in the system. Okay, okay. So basically, if I say the force of the spring, is proportional to the displacement of the spring, right? And here then when we let go of this proportionality sign, we get a constant that we call as the stiffness or the spring constant. Okay. Similarly, when we say the force of the friction, when we talk about the force of the friction, it is proportional to velocity. We are here talking about the kinetic friction. Okay, so this is going to be proportional to velocity. So when we let go of the proportionality sign, we get a constant, and we are going to call it as C. We are going to call it as C, and it is going to be Cx dot. So what will be the unit of C, and what will call this C? What will say this C is? So this C is damping coefficient. What is the C? This is damping coefficient. What is the C? This is damping coefficient. And what will be the unit of it? So it is going to be, what is the unit? So we can always get the unit from the basic formula. So what is the unit of the force? It is Newton. What is the unit of velocity? It is meter per second. So it is Newton second per meter. Is it fine to you or not? Please answer me. Okay. And what is the Newton? Newton is kg meter per second square. Yes or no? Mass into acceleration into second upon meter. So we can also say it is kg per second. Yes or no? Please answer me. Is it correct or not? This is correct only, no? So we have it as kg per second also. The unit of it is kg per second also, we can say. Right? No worries. Okay. Now let's do this way. Okay. So we have previously also tried to apply the D'Alembert principle or the dynamic equilibrium equation To apply the dynamic equilibrium equation, we have given the system some oscillation previously. Okay, but it is a linear system. When it is a linear system, what we are going to do? What we are going to do? Okay, so we have a stiffness, we have some coefficient here. So let me brought it down. Let's imagine that we have this condition and we are holding this mass, we are bringing it down and leave it. Okay, then what is going to happen? When you are bringing it down, what are the forces that are into picture? When you are bringing it down, what are the forces that are into the picture? So you will have to take, when you are bringing it down, so there will be a resistive force, there will be a force of resistance given by, there will be some force of resistance given by the displacement due to the stiffness of the spring and its displacement. So this is going to be Sx. What will be the resistance given by this damper? It is going to be Cx dot. It is going to be Cx dot. Is it fine, beta, everyone? Is it fine to everyone? Please answer me. It is going to be Cx dot. Is it clear, beta? Please answer me. Okay. Okay. Now, sir, where is this mg? Okay, where is this mg? So in this case, we are not considering mg in this case. Why we are not considering? Because when we are applying the spring, when we see the system in this situation, okay, so when you see it in this condition before you move it down, obviously this mass is going to, the weight is going to balance by the force of the spring. Are you getting my point? It is going to be balanced by the force of the spring. Okay, initial displacement of the spring. Okay, so we never consider mg torque. So we have these two forces. So for applying the D'Alembert principle, we can use it like this. So we can put it equal to 0. And since it is a linear system, so we are going to use the formula mx double dot plus cx dot plus sx is equal to 0. I hope it is clear to everyone. So this is what we call as the standard equation. This is what we call as the standard equation of damped vibration system. So we can write it like this: c by mx dot plus s by mx is equal to 0. So this s by mx is nothing but omega n square. Okay, so this can also be called upon as the standard equation of damped vibration system. See, remember this. So in the damped vibration system or forced damped vibration system, it is more of the formula basis. You will see the questions and you will come to understand that if you remember the formula, you will be able to do it. If you do not know the formula, you will not be able to do it. There is not much trick in this. There is not much, not much concepts are there. The only thing is that you must remember the formula. Now, there is one very, very important term in this damped vibration system, that is the friction factor. Okay, or damping factor. We mostly call it damping factor. In the case of vibration, we call the friction as the damping. Okay, so can anybody tell me why we call friction as damping in the vibrations topic? Why we are naming as damping? Why we are not calling it as friction only? So this damping, anyone please answer me in the chat box. Okay, so this damping factor, what we say, it is going to be equal to zeta. We call it as equal to zeta. This is the most important term in the damped vibration system. Okay, so basically just remember this relationship to be concrete. 2 zeta omega n is equal to c by m. Okay, just remember this one. This relationship is very, very important, and this is going to be used in almost all the problems which are in the head of this, which comes under the head of this particular topic. Are you getting my point? 2 zeta omega n is equal to c by m, and now we can do like this. So x double dot. So instead of c by m, we can write this also, plus omega n square, x is equal to 0. X is equal to 0. So this is also one of the standard form. This is also one of the standard form. So none of you have answered why we call it, why we do not call it friction, why we need to call it damping here. What is the reason behind it? I'm expecting some answers. Okay. So this is the standard equation. Now why I have quoted this zeta? Why I have quoted this zeta? Yes, Pranjali. Wonderful. So due to the friction, due to the presence of friction, the vibration in any system, reduces. Okay. Due to the presence of a friction in a system, the vibration reduces. So basically, friction acts opposite to the vibration. It reduces the vibration. And vibration in mechanical engineering, we know that it is not a good thing. We do not want our systems to vibrate. So friction is somewhat reducing or neutralizing to some extent this vibration. So that is why we see it is playing some positive role here. Okay. So friction is, damping is kind of a positive role. Damping is kind of a positive role of a positive name of the friction. Are you getting my point, beta? Are you getting my point? Now coming back here. So we have this zeta, we have this everything. Now what we are going to do? So we have to see some formulas here. So because it is very, very formula basis. So previously we know what is omega n. Acha, I was saying that zeta is the most important term, no? Let's finish that thing first. So zeta, if greater than 1, it is what we call as overdamped system. Okay. And if zeta is equal to 1, okay, that we call as critically damped system. Critically damped system. Okay. And in both the cases, there will be no vibration. If the zeta value is greater than 1 or equal to 1, that is your system is critically damped or the over damped. Okay, we are going to have it, we will be having no vibration in the system. हमारे system में कोई भी vibration फिर नहीं होगा. Okay, and if zeta is less than 1, we will be having the system as underdamped system. We'll call our system as underdamped system. हम क्या कहेंगे भाई system को? Underdamped system कहेंगे. And here there will be vibrations. Okay, यहाँ पे vibrations होगी. There will be vibrations. Okay. There will be vibration. So vibration can only happen in underdamped system where zeta value is less than 1. Okay. And the lesser value of zeta means that there is less friction in your system. More value of zeta means that you are having more friction in your system. Is it fine, I think, to everyone? Okay, now we have to see some formulas here. Let's see some formulas. Okay. So in this, we have to see some formulas. So omega n we already know. It is not going to change at all. Under root s by m. Now, since it is a damped vibration, we'll have to find the omega d, that is frequency of damped vibration system. So it is root over 1 minus zeta square into omega n. It is root over 1 minus zeta square into omega n. Okay. The third formula is, that is very useful also. Okay. So the third formula is ratio of consecutive amplitudes. Okay. So basically, in the case of ratio of consecutive amplitudes, so in the case of damped vibrations, in the case of underdamped vibration, with respect to time, the amplitudes of the vibration decreases. Okay. So if you see the curve of it, if you see the nature of this vibration here, you will find it like this. Okay, so if you are giving it some initial displacement, it would be vibrating like this. So with respect to time, these oscillations are going to reduce and it is going to become zero after some time, right? So basically with every time period, the vibration amplitudes got to decrease. Okay. So this ratio is basically showing you that in one cycle, how much amplitude is getting reduced. So we can call it as x0 by x1. Okay, so what does x0 and x1 refers to? X naught refers to the initial displacement we have given, okay, and x1 refers to after completion of one period, what is the displacement. You can write it like this, x1 by x2 also. You can write it like this, x2 by x3 also. And as you see the nature, this is always greater than this. Okay, the previous previous amplitude will always be greater than the upcoming amplitude. Okay, so what is this going to be? Very importantly, so this is going to be, or we can write it like this, x n minus 1 upon xn. Okay, all are equal only. So it is going to be e to the power zeta omega n td. E to the power zeta omega n td. And what is this td? Capital T refers to the time period. Capital T refers to the time period. So what is this t? What is this td? It is basically 2 pi by omega d. So whenever you have to, what is this time period? It is opposite of hertz only, na? So hertz is omega n by 2 pi. Okay. So hertz is what? Cycle per second. Okay. So time period is what? Second. In seconds, so it is opposite of that Fn. So 2 pi by omega d. Omega n we know, zeta we know. Okay. So this is the third formula. This is the third formula. Okay. Now what is the fourth formula? So sometimes they ask you logarithmic decrement. Sometimes they ask you logarithmic decrement. Okay, so what is this logarithmic decrement? So it is shown by delta, and it is log of e to the power, means that previous thing, zeta omega n td. So this logarithmic decrement is zeta omega n td only. Zeta omega n td only. Right? Right? So these are all the formulas. Now sometimes they ask you this also. Sometimes they ask you this also. What is critical damping coefficient? What is critical damping coefficient? Okay. So we know 2 zeta omega n is equal to C by M. Okay. Now critical damping, at critical damping the zeta is 1. At critical damping the zeta is 1. So C is equal to 2 omega n, okay, by M. Right? Right? Sorry, C by M is equal to 2 omega n. Okay, so when we are placing this zeta as 1, so we can use a subscript of C, so that we can call it as critical damping coefficient. Okay, critical damping coefficient. Okay, so let me write it this way. Okay, so Cc by M, on the same side, it is 2 times omega n. Okay, okay, so what will be this zeta? If you want to define the zeta, you take the ratio of these two equations, you can say it is C upon Cc. So what is this zeta become? Zeta is the ratio of damping coefficient to the critical damping coefficient. So basically, if we talk about underdamped system, we have to get we have to know all these formulas, because many times the questions, formula basis questions are coming. Okay. Okay. So let me give you one question. Okay, let us do one question here. Okay, I'll be writing one question. I'll be writing one question. So we have, okay, so we have M is equal to 2.5 kg. We have M is equal to 2.5 kg. Spring constant is 3 Newton per mm. Now there is one term written here. So amplitude decreases to 0.25 of the initial value after 5 consecutive cycles, after 5 consecutive cycles. All right, after 5 consecutive cycles, so you will have to find the damping coefficient of the system. Find damping coefficient of system. आपको क्या निकालना है? Damping coefficient of system. ठीक है, आपको damping coefficient of the system निकालना है. Is it fine बेटा? निकाल पाएंगे? Okay, let's try to find it. Okay, शुरू करिए. Let's try to find it. Let's see if we can do it or not. Let us see if we can do it or not. Please go for it. Let's see if we can do it or not. Let us see if we can do it. Gautam, you have to find damping coefficient, that is C you have to find. Remember, you have to find C. Okay, and the answer you are giving is not correct. The answer that you are giving is not correct, it seems. What about the rest of you? Please try answering it. Let us try it. Yeah, Gautam. It seems to be correct. What about the rest of you, beta? What about the rest of you? Yeah, Gautam. Correct. Wonderful. What about the rest of you? So what is given in the question? So we have the mass, we have the stiffness. Amplitude decreases from 0.25 of the initial value after 5 consecutive cycles. Okay. So basically what is given? What is given here? 5 cycles. So cycle start from x0. x0 to x1, one cycle is completed. x1 to x2, this is second cycle. This is third cycle. This is fourth cycle. And this is going to be fifth cycle. So first cycle, second cycle, third cycle, fourth cycle, and fifth cycle. So what is given here? What is given here? Amplitude decreases to 0.25 of the initial value after 5 consecutive cycle. After 5 consecutive cycle. Acha Shrikant. Okay. Okay. No worries. Okay, so after means what? After means that initial value is what? Initial value is x0, and after the fifth cycle means that you are given that x5 is 0.25 of x0. I hope you realize this. I hope first of all we realize this thing, that x5 is given to be 0.25 of x0. Is it clear, beta? Please answer me. x5 is given to be 0.25 of x0. Is it clear, beta? Please answer me. Okay, so from here we can write x0 by x5 is equal to 1 upon 0.25, right? 1 upon 0.25. Now, how to deal with this kind of a data? Okay, so we have x0 by x5 is equal to 4. 1 upon 0.25, I think it is equal to 4, right? I think it is equal to 4. Okay. Now, how to deal with this situation? How we can deal with this situation? So, this is x0 by x1. Can we write it like this? x0 by x1 into x1 by x2 into x2 by x3 into x3 by x4 into x4 by x5 is equal to 4. Is equal to 4. Can we write this way? Obviously, yes, sir, we can write this way. Xn minus 1 upon xn. Again, xn minus 1 upon xn. So, all these are nothing but equal to e to the power zeta, omega and td. So, you will have to write e to the power zeta, omega and td, e to the power zeta, omega and td, and you will have to write it 5 times. So, simply we can multiply it with 5. And it is equal to 4. It is equal to 4. Now what can be done? Now what we can do? We can take the log both of the side. Can we take the log both side? Yes or no? है ना? So if we take the log both of the side, we will be getting zeta, omega and td is equal to log of 4 divided by 5. Is that fine to everyone? Please answer me. Is that fine to everyone? Please answer me. Bolo na bhai. Please answer me. Right. So you will say, sir, how we are going to proceed from here. In this equation, we can see that we are having 3 variables. In this, we are seeing that we are having 3 variables. So it is not actually 3 variable. It is 1 variable only. How, sir? So we are having zeta, omega and td. Td is what? 2 pi upon root over 1 minus zeta square, okay, into omega n, okay, is equal to log of 4 upon 5. So from here, omega n will be cancelled out, and you are left with only 1 variable, that is your zeta. So you can find your zeta from here. Can you find your zeta from here? Yes or no? I think yes, sir. We can all find the zeta from here. Whatever it is coming out to be, you can keep it with you. Okay, and also if we can find the zeta, so we also know that 2 zeta omega n is equal to c by m. Now you have the zeta. For omega n, you are given with s and m. Both are given. So you have omega n also. M is also given. So only 1 variable, that is c. And when you try to find it, you will be getting 7.6. So 7.65 something. So why you were not able to answer it? Dheeraj, Pranjali, Shred, And the rest of you, only Gautam has answered it correctly. Why we were not able to answer it correctly? What is the reason? What is the reason? Is it clear now? Please answer me. Is this thing clear to everyone? Please answer me. अरे बोलो ना भाई. Is this thing clear to everyone? Please answer me. Okay. Okay. Now one last type of, so in this we can apply the torque method also in the same way. Okay. But when we have the damper, always remember to take the force proportional to the velocity, that is x dot. You will have to make the equation like the standard generalized equation, and then what you can do, and then you can compare. Acha Pranjali. Okay. Okay, so do practice. More practice is required. All of you, see, I always suggest you guys to make more practice. Okay, try to practice it more. We are always here for you. Okay, okay. Wherever you need any assistance, you can always contact me. Okay, so but do practice a lot. Okay, take up the test series, everything. That is how we can proceed. Okay, now coming to the last. The last one is force damp vibration. The last one is force damp vibration. This is completely formula based. I would say that in this particular topic, you get the marks only due to if you have the capability to memorize bigger formulas. अगर आपको लंबे लंबे चौड़े चौड़े फॉर्मूले याद करने की कैपेबिलिटी है तो आपको इस पर्टिकुलर टॉपिक में मार्क्स मिलेंगे, अदरवाइज नहीं मिलते हैं. आर यू गेटिंग माय पॉइंट? So basically this topic gives you marks on the basis of your capability of memorizing bigger formulas. So in the force damp vibration system, simply I am going to give you, there are three formulas. Basically there are three formulas. One is of amplitude. Okay. One is of amplitude, and how this force damp vibration system would look like. So it is basically, so this is your natural vibration, only spring and the mass. This is your damp vibration system, that is spring, damper and the mass. And what is your force damp vibration system? So you have a periodic force applied to it. You have a periodic force also applied to it. Okay, so it could be F naught cos omega t or sin omega t, that doesn't matter. All right, that doesn't matter. Okay, that doesn't matter here. Okay, so again we can do all these things, but I'll be coming to the point as this is the score booster session. So we are here to mention the important concepts and the formulas. So the first formula is of amplitude. So it is going to be F naught by S. F naught is the initial, maximum magnitude of the unbalanced force, which is also periodic. So it is going to be F naught by S divided by all right. So this is your amplitude. Okay, this is your amplitude. Okay, so the second thing is your magnification factor. Your magnification factor. This is nothing but A upon F naught by S. So in the previous formula, if you cancel this F naught by S down, just delete it, okay, and put it equal to 1. This is your, this will become your magnification factor, right? So I'm not going to write it down again. Okay, so I hope you can do it by yourself. Okay, and the third important formula is transmissibility ratio. And also there is a graph to transmissibility ratio that also you must understand. Okay, but numerically, if we talk, these are the three formulas here. So transmissibility ratio, we normally show it like this, and this is the ratio of transmitted force to the original force. So it basically giving you insight in the vibration isolation, that how much of the vibration is transmitted to the ground, what part of the force that is generated due to vibration reaches the ground. So it is Ft by F naught. And what is this transmissibility ratio? It is root over 1 plus 2 zeta omega by omega n whole of a square divided by root over 1 minus omega by omega n whole of a square plus 2 zeta omega by omega n whole of a square. So basically, if you are asked a question here, if you are asked a question from these topics, you will have to apply these formulas and you will have to get the answer. Okay. So this is the thing in vibration. So let's begin with the quiz now. Let's conclude the session with the quiz. And see, it is impossible. It is definitely, this is a very big subject, no? Theory of machine. It is impossible to do all the topics, but we tried to cover as, so today I wanted to do with some balancing also, but the time do not allow. So please join the quiz, guys. Let's join the quiz now. Okay, we know the how to play the quiz. You have to go to this link. Okay, just go to this link to join the quiz. Okay. There is no negative marking here. Every question is assigned some points. Tougher the question, more are the points, and definitely if you answer in lesser time, you are going to get more points. Okay, please join, guys. You will have to go to the link like daily we do. Okay, okay. Let's join the quiz. Let's join it quickly. Okay, so let's see how many of us have joined till now. Okay. So I hope you guys, so before I start with the quiz, I want to ask you something. So did you find this sessions good till yet? Okay. Okay. Are you gaining something out of these sessions or not? Right. This is somewhat a quick revision we do here. We try to do here. Yes or no? All right. So from tomorrow, same timing, 7 p.m., we are going to start with the industrial engineering. So there is a one square is missing in this formula. Let's answer. So just remember there is a square here. Okay, there is a square here also. Okay, it missed. Okay. Let us see. Let us see if we can answer it. Let's see if we can answer it. So I hope all of us are having a good time here in the School Booster, and from the tomorrow session we are going to start with industrial engineering. Okay, I'll be only taking that. Okay. So I think many of you are our home gate students also are joining in the session. So you will be getting a different outlook of the subject. Okay, because I think many of you have learned this theory of machine design, fluid mechanics from me only. Okay, in the regular sessions also. So only one correct answer of Shred. What was the question? The question was that the amplitude of this force damped vibration system decreases, increases, or remain constant with time. So if you know that in force damped vibration system, the amplitude is only due to the particular integral. किसकी वजह से होता है? If you remember the derivation, एक होता है कॉम्प्लीमेंट्री फंक्शन, एक पर्टिकुलर इंटीग्रल. जब हम डैम्प वाइब्रेशन सिस्टम में होते हैं तो केवल कॉम्प्लीमेंट्री फंक्शन कंट्रीब्यूट करता है वाइब्रेशन में. कॉम्प्लीमेंट्री फंक्शन समय के साथ खत्म हो जाता है, लेकिन पर्टिकुलर इंटीग्रल जो केवल इन फोर्स डैम्प वाइब्रेशन के केस में होता है वो कभी डिक्रीज नहीं करता है. तो फोर्स डैम्प वाइब्रेशन में जो एम्पलीट्यूड होते हैं वो हमेशा टाइम के साथ कांस्टेंट रहते हैं. ओके, लेट्स गो टू द सेकंड क्वेश्चन. प्लीज ट्राई दिस वन. I hope we can do this. In the recent GATE examinations, you may see these kind of questions a lot. You might have seen all these kind of questions, the rolling problem. Many of us may do it with the energy method also, but I recommend the torque method. Only one answer till now. Is it done? Only two answers till now. So when we have pure rolling, what we can do? We can assume a hinge. So we can do it by the torque method. Okay. So we can assume a hinge at the point of contact, which is the instant center. Okay. Give it a oscillation. Take up the forces due to the springs. Okay. And then follow the same procedure, apply D'Alembert principle, and you will be fine. So I see that none of you have given the correct answer. Chalo, coming to the third question. So this is a question of balancing. So it is a MSQ question, multi-select question it is. More than one option you can choose. It is not a MCQ question, it is a MSQ question. Okay. So balancing we couldn't touch in the score booster session, but I think you can still attempt the question. So remember, we have learned something like secondary balancing. Okay, so what is the secondary unbalanced force? Acha Pranjit, no worries. If you have done it correctly, then it is okay. And in GATE examination, the range, they have better system. Okay, we are working on it. Okay. So I see, okay, none of you could completely answer it. So remember secondary forces. If you remember, what are the secondary forces? M R by 4n 2 omega square cos 2 theta, right? This is how we can relate it with the primary. And if all the masses are in the same plane, we can balance it by single mass only. Okay. Now coming to the last question for the quiz. And after this question, we can end this session. So it is basically about the transmissibility ratio. There is a graph of transmissibility ratio with respect to omega by omega n. We have a graph also with transmissibility ratio with respect to omega by omega n. Okay. So if you understood the graph, then only you can answer it. If you know the graph, then only you can answer this. Okay. Let's see how many of us can answer it correctly. Please read the question. Please try to recollect what we have learned in the graph of transmissibility ratio versus the frequency ratio, omega by omega n. Okay, do we remember that we have a plot between transmissibility ratio and omega by omega n? Do we remember that? So today with this question, our score booster theory of machine sessions will be ended. I hope you guys found these sessions useful for your preparation, right? We are trying to cover as much as we can. It is a continuous 3-hour session every day that I am taking for you guys. Okay, I hope you find it useful. Okay. Okay. Okay, so everyone has answered it. Let us see the result then. Okay, so okay, Pranjali was able to answer it correctly. Okay. So today Shred have topped the chart, and Gautam and Dheeraj, please do practice the questions more. Okay guys, so thank you very much. I think this we can call it an end for today's session, and this was the Shred notes is updated, I think, in the YouTube link. This all whatever we have written here, this is going to get uploaded, okay, in the YouTube link only. Okay, you check the description. So I guess you will be getting that. Okay. So guys, I am hoping that you found these sessions interactive and you found this session useful for you guys. And with this, we are ending the theory of machine score booster sessions. I tried to cover as much concepts as possible. Simple mechanism we have covered. Okay, sure. The technical team will look into it. Okay, if you are not able to find. Okay, Pranjali, I'll get it done. Okay, I'll ask the technical team for it. Okay. Okay, so we have done it the simple mechanism, velocity analysis, acceleration analysis. Yeah, Dheeraj, do practice better. Gears, gear trains, flywheel, and now vibration. So we were not able to touch the balancing part, the governor part, dynamic analysis, gyroscope is there, balancing is there. So they are also good topics, but as you understand that it is not like I could do one thing, I could write the formulas of everything. Okay, that I couldn't find. I didn't find it good way. So whatever I have taught, I tried to teach it so that you will understand it more. And if any one of you is seeing me for the first time also, who is not my student also, may get something out of this videos. Okay, so with this, tomorrow 7 PM we are going to do with the industrial engineering part. ठीक है, industrial engineering शुरू करेंगे कल से स्कोर बूस्टर में. ठीक है, प्लीज ट्राई टू डू ज्वाइन द लाइव सेशन. ओके, आप में से मेरे ख्याल से बहुत सारे लोग या धीरज, आई एम गोइंग टू कंटिन्यू टुमारो आल्सो विद द इंडस्ट्रियल 3 days and will try to cover as much as I can, okay, in that also. So I think many of you might not have read this industrial from me, so do join. posting. Gautam, I'll try to. Pranjali, tomorrow we'll be starting with inventory control. So in industrial, my agenda is in the first session I'll try to cover inventory control. I'll try to cover the forecasting, and I'll try to cover the bill of material. These three topics is in my agenda in the first session. In the second session, I'll try to cover part and CPM and sequencing. Okay, and in the last topic, I'll try to cover the linear programming. Okay, you know that these are the big topics. Okay, so we'll try to do that. So tomorrow we'll be starting with the inventory control. All right. Okay. So hope to see you guys again in the next session of Industrial Engineering Score Booster session, and we'll see you in the next session for sure. And thank you very much for watching. Do not forget to like and subscribe the channel. Thank you very much.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster will definitely boost your score. So thank you once again.
Hello students, thank you so much for watching the session. We hope you enjoyed this session a lot, and there are many more sessions to go.
So do like, share and subscribe to our YouTube channel, and this GATE score booster